Alrighty, there seems to be something a little goofed up with my camera here, but we'll try to get through it. I just wanted to do a video on how to solve the test problems that I chose for you, and we're going to start with the 2012 problem, the mass in a spring problem. And they give you some information. They tell you that the mass of the block is zero point 0.3 kilograms, and that it is pulled away from its equilibrium position. Um, at time equals 0, and then they have a graph of the velocity that's going to happen. And let's just take a look at this graph of velocity. We're going to start with 0 velocity, and that's appropriate for when you pull something to the side and let it go. We're then going to go into negative velocity, and that's because they want the positive direction to be to the right, so this thing initially goes back to its equilibrium position by going to the left. We can also see that the maximum velocity that we get in this negative direction looks like it's right there. This is 0.1, this is 0.2, so that is 0.16. So negative 0.16 seems to be our maximum velocity. Then we're going to return to the equilibrium position, and I'm sorry, not the equilibrium position. This is a graph of velocity versus time, and now you can see how easy it is to get yourself confused in this business. The velocity will return to 0. That will happen when we're on the other side of our equilibrium position. And then we're going to speed up, and as we go through our equilibrium position, we're going to have a maximum speed over here of positive 1.6. So we can see that V max is going to be 0.16 meters per second. Another thing we can see off of this graph is how long it takes to complete the motion. We start here, and this is the next time that we're back in that location. Now, how do I know? Well, because that is one period of the motion, and that takes place in 0.7 seconds. So it looks like the period of our motion is 0.7 seconds. These are all things I can get off the graph. And again, very important that you remember this is a graph of velocity versus time. And they kind of help you a little bit because they're going to ask you some questions, and they're going to start by asking you about the velocity versus time. So let's go ahead and get a piece of paper here, and I'll leave this up so you can see what we're doing. But we are attempting to derive an equation for velocity as a function of time. Now, I'm going to brainstorm a little bit. I remember that the solution for this kind of stuff, the position as a function of time, is going to be some amplitude, and then that's going to be times cosine of omega times t. And I don't know what the amplitude is of the motion. You could get it off of this drawing if they'd given you this maximum distance, but they didn't. And we need to figure out what omega is in this situation. Furthermore, know that the velocity as a function of time is the first derivative of this. Okay, that means that we're going to have an a and an omega coming out because when we take the derivative of the argument of cosine, and derivative of cosine is minus sine, so that's the function. And if I was being asked for acceleration as a function of time, I could probably cobble that together. That's probably minus a omega squared back to cosine, and I ran out of room just like a ASB student making a sign. Okay, so this is the form of the equation, and indeed this velocity looks really good. Well, because I started with the situation of the block being pulled to the side in the positive direction using a cosine, you're going to get a negative sign, and that's exactly what this graph looks like. It's a negative sign. That means that the maximum velocity is this thing right here, a times omega. So from this, I can actually figure out what a is if I knew omega. But omega is related to the time. Now, we do know that, let's see now. We know that omega equals square root of k over m. Of course, they didn't give us k, so this will be useless to us. We know that the period is 2 pi over omega. And we know that the frequency is omega over 2 pi. Now that's interesting. This one is very useful to us because we do have the period, so we can find omega. Excellent. Oh, we're cracking this nut really fast. All right, so utilizing this piece of information, we're going to say that the period, which is 0.7, is equal to 2 pi over omega. This way, omega is 2 pi over 0.7, and now we can actually just come over here and we got what was our other thing that we were going to do? A times omega. Okay, V max, and that's 0.16. Okay, so we also know that A times omega equals 0.16. Now that omega is 2 pi over 7, A times 2 pi over 7, 0.7 Harmon, equals 0.16, we can figure out that A equals something. Okay, now I don't know if I want to leave this 2 pi in here. Let's get actual numbers for these things. Omega is going to be 2 times pi divided by 0.7, and that looks like 8.975. Why 8.97? I'm just going to call that 9 radians per second. Okay, good. And now that that's over here, so A times 9 equals 0.16, so 0.16 divided by 9 equals, it looks like A equals 0.1777, so let's call that 0.018, and that's amplitude is going to be in meters. Okay, so I have some information. I got it from the graph, from the physical extent of the graph, finding the period and the maximum velocity, and knowing what the equation looked like. And now I can answer part A. Part A, the answer to part A is that velocity as a function of time is going to equal negative 0.16, because that's what Vmax was. And now I see what's wrong with my camera. It's way too close. Much more space to work with here. Okay, times the sine of, and now we need omega t, 9 times t. So there's my answer, and I not only have the trigonometric function that I need here, but I also have the two numbers that go out front, and that's what they said. They said including numerical values for all constants. Had a couple people who left a's and omegas and stuff in their equation, and you cannot get full credit from the College Board under those conditions. Now we're going to move to part B. Well, part B, we're ready to just we're just ready to go ahead and write it down, because we have the form of the equation. So x as a function of t is going to be a, which we said was 0.018, times the cosine of omega t, which is 9 times t. And there we go, another one. So we really did all the hard work earlier by taking a look at this graph and getting stuff off of it that would allow us to calculate our two constants that go in the equation, these two things right here. And finally, calculate the value of k. Well, we can go back now to our definition here, and we can say omega equals square root of k over m, and we figured out that omega was 9, and that's going to be the square root of k over 0.3. Looks like we're going to square both sides, so 81 equals k over 0.3. So I need 0.3 times 81. 0.3 times 81 equals 24.3. K is going to be 24.3. Probably can't keep all these digits because I rounded off so much out of the 9, but I don't believe that the, let's just keep 24. 24 newtons per meter. Okay, so then we go C. K equals 24 newtons per meter. This whole shebang-a-bang was worth 8 points. There were points for having the correct trigonometric function. There were points for sorting out what omega was, points for getting the right coefficient in front. For the velocity, it's the amplitude of the graph of velocity, and for position, you had to figure out what A, amplitude of the motion, was from knowledge of simple harmonic motion. So this was intricate, this was tough, and really wasn't worth a whole lot of points. Most people did pretty well. I'd say the average score was a 6 on this one, maybe 5.5, 6. We'll see. Not bad. Okay, so, oh my, I have totally marked up my piece of paper here. Let's go get a fresh copy. So now let's talk about this skier problem. The skier problem is a little bit more intricate. So they set up a thing where there's a skier going down a hill. He has a massive capital M. They're not going to give us numbers. That's going to be one of those problems, huh? Skier starts from rested at time 0 and subject to a velocity-dependent drag of the form F equals minus BV, where V is the velocity of the skier and B is a positive constant. Express algebraic answers in terms of M, B, theta, and fundamental constants. Okay, I'm going to take down the hill. I'm going to take that to be the positive direction. Certainly some of you did not do that, and well, whatever. We'll figure it out as we go. Now we need to go ahead and draw a free body diagram for the skier, and this is going to be a typical inclined plane free body diagram with a normal that is perpendicular to the plane. I don't like this red pen. I need to put this one aside. I think this other one is sharper. And there's going to be weight straight down, m times g. And then because he's moving to the right, I assumed his gender. Moving to the right, we're going to have a drag force, which is going to be straight up the plane. And I'm going to write that as b times v. You could have written F drag. One thing that's really important is that your drag force be along the plane, that your normal force be perpendicular to the plane, and that the weight be straight down. It is also not appropriate to componentize weight. The College Board has said over and over again that they want you just to draw the forces on a free body diagram, not to componentize them. Now, I need to componentize them because I'm doing a problem where the components are important. So I might draw a second free body diagram over here for myself, or do this on a piece of scratch paper. And I'm going to componentize the weight. So this one is BV, this one is the normal. This part is mg cos theta, and this one over here is mg sine theta. And once again, if you don't know that the sine theta portion is the portion that's pulling you down the hill, you need to go back and review your inclined plane problem. Okay, part B, write a differential equation that can be used to solve for the velocity of the skier as a function of time. I'm just going to go ahead and go right down here and do that. F net equals m times a is how we start all of our differential equations. Now the net force is going to be the net force in the horizontal direction. So that's going to be mg sine theta minus b times v. And that's going to equal m times a. Okay, we have an algebraic thing we can clean up, and there's a differential thing we need to do. The algebraic thing is we can divide through by m. That will simplify things, and that gets m off of this side of the equation, which is a good idea because this side of the equation is the side that we're going to turn into a derivative. Now, when this function was an x over here on this side, we wrote a as the second derivative of x with respect to t. But because the function on this side is v, I'm going to write a as the first derivative of v with respect to t. And that's going to give me g sine theta minus b over m times v equals dv dt. And this is a solvable differential equation. And because I multiply or divided through by m, it is in a very pretty format. And they were originally going to ask you to solve this thing in part D. But before we do that, we have part C to worry about, determine an expression for the terminal velocity of the skier. There's a number of different ways to think about this, but my favorite way to think about it is the terminal velocity occurs when the net force is 0. And that means that mg sine theta, the force down the plane, will be equal in magnitude to bv, the force back up the plane. And that happens at a certain velocity. And we can find that terminal velocity by simply dividing through by b. So we're going to have mg sine theta over b. A number of people had memorized this from the previous example where we just dropped something and it wasn't on an inclined plane, and they left off the sine theta. Okay, that brings us to solving a differential equation. Well, we're not going to do that. I asked you to solve a slightly different problem. I asked you to graph the velocity and the acceleration as a function of time. We're going to refer back to some of these numbers. I'm going to put this piece of paper up here. All right, so what do we got here? We need a graph of velocity, as a function of time. Okay, let's make the axes. There we go. So we know that the velocity of the skier starts at 0, so that's where one point is going to be. And we know that it's going to get up to an asymptote that happens to be at Vt, the terminal velocity. Now, I think it's acceptable to go ahead and label that as Vt because you previously defined Vt here. But if you're really worried about getting maximum points from the College Board, you might want to label this as mg sine theta over b, which is what Vt was. And now the shape of the graph, it's an exponential curve that's been flipped over. In other words, it's a decaying exponential that goes asymptotic to this guy. So it has this kind of a shape to it. And that's all you really need to do. You've shown that it touches at 0, that it's asymptotic to Vt, and you've got a nice graph of velocity versus time. Some of you flipped this graph over because you were treating down the ramp as the negative direction. That's perfectly acceptable. Now, if I want to make a graph of the acceleration versus time, and I didn't need to put that t there. That's what I was complaining about. That's going to start with our maximum acceleration, which is g sine theta. And then it's going to have a decaying exponential that becomes asymptotic to 0. So I would make that kind of a graph. That's the shape of it. The acceleration plummets until the force is shrinking to 0, and then the acceleration kind of peters out to nothing, and we get our terminal velocity. So a few people didn't put the sine theta here. A few people called this mg sine theta, and I was forced to take points off for that. It really broke my heart. There were 12 points available for this particular problem. 3 of them on the free body diagram. I cannot remember how many were. Let's see how that worked out. 3 for the free body diagram, 4 points for the differential equation writing. 3, 4. No, 3 points for the differential equation writing, 2 points for the terminal velocity finding, and 4 points for the graphs. 1 point for this, 1 point for that, and 1 point each for the shapes of the graphs. So that's how that turned out into 12 points. So that's how to solve these problems, and that's I'll refer you to this later.